For this example, example 5, it says find the simplest form for the fraction a squared minus b squared over 4a minus 4b, and then also we're going to do the other one. The other fraction is 6x squared y over 75 xy squared. Okay, now we're still using the same idea that we did in example 4, but actually we have to do the prime factorization this time because we have variables and all kinds of things going on. So looking at this very first one, I'll do this one in blue. Look at the a squared minus b squared. Do you remember us working on a little bit of factoring in the last chapter? And we talked about a difference of two squares. This is a difference of two squares, and so it will factor into a plus b times a minus b. Now on the bottom, we have a common factor of 4 that we can reverse distribute, or factor is the same word, which would be 4 times, and then we'd be left with a minus b. Now, just like we did with example 4 in that prime factorization, anytime you have a factor over a factor that is the same, it's the same thing as saying 1. So this a minus b over a minus b, that's really just a big old 1. So all we're left with now here is a plus b over 4. So that would be our simplified version of that fraction. In the next one here, we have our 6x squared y over 75xy squared. Now we could write this all out if we wanted to. We could say, well, let's see, 6, that's pretty easy to do the prime factorization. That would be 2 times 3, and x squared would be x times x, and then y would be just y. So that would be its prime factorization. For the 75, we may want to go ahead and do the factor tree just so we can see it. 75 would be 3 times 25, and 25 would be 5 times 5. So when I wrote that as its prime factorization, it would be 3 times 5 times 5, and then we would have a times x, and then we'd have times y squared, which would be times y times y. Now we're looking for those common factors in the numerator and the denominator that we can divide out. So we have a 3 on top and bottom, which would be a giant 1. We also have an x on top and bottom, which would be a giant 1. And we have a y on top and bottom, which would be a giant 1. So what we're left with on top is just the 2 and the x. And on bottom, we're left with 5 times 5, which is 25, and then times y. So we can do it just like that. Now, another way that we could look at that, if we wanted to, would be using our exponent rules that we've talked about before. So we could do that too. We could look at 6 and 75 and say, well, I know both of them are divisible by 3, so 3 goes into 6 2 times, and 3 goes into 25, or 75 25 times. Now then I have an x squared on top and an x on bottom. So when we divide like bases, we subtract the exponents. 2 minus 1 would leave us with just 1x. So that would leave us with just an x on top. Here on the y's, we've got y to the first and a y squared on bottom. So when we subtract those exponents, that would leave us with a y on bottom. So what we're actually left with now on top is a 25x, I'm sorry, a 2x, and on bottom we're left with 25y. So we would get the same thing no matter which way we looked at it, but if you need to see it with the prime factorization, go ahead and do that so that you can see all of those ones that are happening, which is the proper way of saying. I know we say canceling, but that's not really proper. They don't just disappear. The reason that you can cancel them is because they're technically ones. For example, 6, this says, are the fractions equal or not equal? Well, there are a couple of different ways that you can go about trying to figure this out. You can make sure that both fractions are completely simplified and then see if they're the same. Um, and another way is a cross multiplication technique. So we're going to do it both ways so that you can see both of these methods and you can pick for yourself which way you like to do it the most. But I do want you to see both ways. Okay, so let's look at the 11/12 first. Um, there is no factor that these have in common. I mean, the 11 is not divisible by 2 or anything else. It's actually a prime number. It's 1 times 11 are the only factors. So since there are none of those in 12, this is in its most simplest form. But 110 over 168 is not in its most simple form. In fact, we can divide top and bottom by at least 2 because they're both even numbers. So when I take 110 and divide it by 2, we get 55. And when I take 168 and divide it by 2, I get 84. Now, looking at 55 and 84, the only factors of 55 are 1 times 55. Let me write them up here. 1 times 55. 2 doesn't go into it. 3 doesn't go into it. 4 doesn't. 5 does. 5 times 11. Those are the only factors of 55. So none of those factors exist inside of 84. So both of these now are in its most simplest form, and they do not match. So these are not equal fractions. Now, another way to look at that would be what we call a cross multiplication technique. If they are equal, then when you multiply them crisscross pattern, those multiplications, those products will be the same. So if I multiply 11 times 168, it should equal 12 times 110. So let's see, 11 times 168, that would be 1,848, and 12 times 110 would be 1,320. So that is another way of proving that those things are not equal. Either way, let's try it on this problem here. We have 30 over 75 and 24 over 60. Now, I do know that 30 over 75 can be reduced down because one ends in a 0 and the other ends in a 5. So I know I can divide top and bottom by 5. So when we do that, 30 divided by 5 would be 6, and 75 divided by 5 would be 15. Now we're not done because 6 and 15 both have another common factor. 6 can be divided by 3 and 15 can be divided by 3. So 6 divided by 3 would be 2, 15 divided by 3 would be 5. So this is the most simple form. Alright, now let's look at the 24 over 60. Again, I know that at least 2 will divide into both of them because they're both even. So 24 divided by 2 would be 12, and 60 divided by 2 would be 30. Now here again, I know I can still keep dividing into these because 12 is divisible by 3 and so is 30. So if I divide 12 divided by 3, I get 4, and 30 divided by 3, I get 10. But this is still not in its most simple form. I can still divide both of them by 2. You don't always have to find the biggest thing every time. You just have to find something that will divide into both of them and keep making it smaller. So 4 divided by 2 would be 2, and 10 divided by 2 would be 5. Now look, these are the same exact fraction. So these actually are equal. But let's verify it with our cross multiplication technique. Okay, our cross multiplication technique would say 30 times 60 should equal um, 75 times 24. I know I'm running out of room over here. So 30 times 60, that would give us 1800. And 75 times 24, well, that would also give us 1800. So that verifies that those are in fact equal. No matter which way you look at it, those are equal fractions.